My name's Dave Joyce. I work for Husco International. I'm a product engineer. I look after the suspension group. I'm here to talk to you today about front axle suspension on tractors. So, a brief overview of what I'll be talking about. Looking at basically the history of Husco with suspension, a little bit of background, the effects of vibration on a tractor, so why you would want suspension, bit of an overview in different suspension systems, basic functionality of how they work, regenerative systems or regen systems as they're also known, semi-active systems, double acting systems, cab suspension, and a little touch on loader boom suspension as well. So Husco, we first got involved with suspension valves back in around about the turn of the millennium on the Mercedes ABC system, which is active body control on their SL models. We then, realising the potential, moved into agricultural suspension, probably in the infancy of production suspension valves on tractor front axles. We currently supply over 31% of front axle systems worldwide. We're a preferred supplier on C&H ag platforms. We also supply to Massey Ferguson, Valtra and Claas, I think possibly some others. The effects of vibration. So the obvious thing is, of course, operator comfort, but in terms of manufacturers of machines and people who buy machines who aren't owner-operators, they might not particularly care about that. But fatigue and injury are serious concerns. The more vibration someone's going to experience sat in the seat of a tractor, the more tired they're going to get, the less productive they're going to be, the less hours they're going to be able to work, essentially, and the less money they're going to make back off the machine. And there is, of course, danger of injury. So there is legislation, European legislation, in place to protect operators from that. So the graph here shows weighted acceleration. This is the measure of the vibration experienced by the operator. Now that's weighted based on its various components of accelerations in different planes. So forwards, backwards, up, down, left, right, and there's different weightings associated based on the effects that they actually have on the human body. And then that plotted basically against how long you can be exposed to that. So obviously higher levels you can be exposed to for a shorter amount of time without any real concern. So the green line here is at what point someone's supposed to take action to levels of vibration. The red line is the absolute hard limit. Now I've got to say, I'm not too sure what the actual penalties for exceeding this, nor how it's enforced, but it's certainly something that manufacturers use to try and tune their machines and as a margin to aim for. Typically practicing with a machine, testing a machine on an ISO track, which is a standardised bump track essentially that will be the same around the world, and looking to make sure that the vibrations are down within a certain level when driving at a certain speed over an ISO track, and they can then use that as very much a measure of how well their machine is compared to competitors or previous machines. This chart here is an explanation. This comes back from the early days of ag suspension. It's basically the white bar here is how fast you can go doing different activities with a traditional rigid machine, and how fast you can go with a suspended system. So this is an fairly early day system, but it's fairly basic, but it's suspended front axle and suspended cab. So, for example, in transport, there's an additional 44% of speed. So you can drive faster. You're going to be getting your job done quicker. You're going to be more productive. You're going to make more money. Which is ultimately what a lot of the people buying machines. That's what they're looking for. So ultimately, the role of a suspension system is to separate the operator from the vibrations of the wheels, leading to productivity increases. So why would you use hydro-pneumatic suspension? So I mean, traditional suspension systems on a car, for example, you've got a fixed viscous damper, just a cylinder with a piston with orifices in it. So that as the piston tries to move through the fluid, it's just restricted. Oil has to push across the orifices, slows it down, takes movement out of it, takes energy out, kinetic energy, and turns it into heat energy, and a spring to actually absorb and rebound the impact. Now you can't use that on a tractor, largely because the load changes that it'll see. Because you'll be mounting it up with different implements front and back, ballast weights to compensate that. You could be putting extra tyres on, you could be putting water into the tyres, I believe, is something that people do to give you extra grip. So all these things to change the loading that the machine sees. That also all means that you're going to have a different load set acting on the suspension. So if it's much heavier, it's going to sink down. It's going to not respond as well. Also, it's going to change the height of it. So you're going to want something in there to be able to level the suspension. So a couple of functions that you can't get from a standard automotive system. In terms of why hydraulics and not just purely an air system, which you can do, well, air compressors aren't standard on many tractors, the majority of tractors, to be honest, whereas hydraulics are. So you've already got the system in place. A pneumatic system also involves a viscous damper, similar to what you'd have on a car, in order to do the damping. Whereas with a hydraulic system, you've got it all integrated. It's all in the one setup. You can also achieve variable damping much easier, which gives you much more control and improved suspension. So in terms of basic functionality, the first main function is to reduce vibration. So two elements of that is the accumulator. So that's gas over oil, typically nitrogen filled with, being inert. Over oil accumulator. Now, varying pre-charges on the air side will give you different spring rates. And that solely acts as the spring functionality. The damping is then provided by some sort of orifice. So oil is pushed across the orifice, heat is generated, a pressure drop, and some of the movement will be reduced as a result of that, and the kinetic energy is dissipated as heat. You need a levelling function to make adjustments to the ride height. Now, you can have systems that will operate up and down at the operator's will, but the main reason is to keep you in the middle of your suspension travel, to make sure that you've got the maximum efficiency you're gaining from the size of the cylinders you've got and the system that you've got. So if you put on a really heavy weight and you sink right down to the bottom, it's only going to take a very small bump before you're going to hit the end stops. So you always want to be in the middle there. Typically you also want a lockout function. So on numerous operations you might try and do where you want sort of fine control, particularly with a loader front end on a tractor, for example. You're trying to pick something up very carefully. You don't want to be bouncing up and down. So you have a system to lock the suspension solid. Also, when ploughing is probably a reasonably big one with the tractor. So a number of different ways of achieving hydropneumatic suspension. So the chart here shows approximate system cost versus a performance score. So we've got a traditional automotive style system shown here, just sort of for reference. We've got the blue line is regenerative systems. So from the basic to a dual rate to a semi-active regen system, and then you've got double acting systems shown in red. So the increasing complexity will give you an improved system. It'll cost you more money at the end of the day. Now the performance, how we'd look at that is how it performs across the load range. So as from a low weight on the front axle to a high weight, you kind of want it to give you equally good performance. That's not usually the case. So the better you can achieve that, then the better the suspension system's going to score. Particularly at really low loads. So on a tractor with a very heavy implement on the back, you can have a very minimal front load, and that's really when it gets particularly difficult to control the suspension. Largely because your accumulator will have a pre-charge. That pre-charge gives you the spring rate. If that pre-charge is 30 bar and your pressure on your suspension goes below 30 bar, you have absolutely no spring rate anymore. So the lower that gets, then typically the worse it gets. General ride quality, which ultimately it comes down to what does the operator think when they're driving it in many cases, and if he doesn't think it's any good, then he's not going to buy one of those tractors again. He's going to complain to his mates and all the rest of it. Right? But ultimately, with accelerometers and ISO tracks, etc., we can really quantify that, and manufacturers particularly can look at very incremental changes and see improvements. Then there's the ability for it to lock out. Some more basic systems can just lock down at the bottom end of travel or at the top end of travel. Improved systems can lock in the middle or even give you locked out to wherever you choose for whatever reason. The regenerative system, so this is a basic Husco regen suspension system. So this chart here, this shows the change in front axle loading. So very small text here, I appreciate. This is 2,000 kilos, 4,000 up to 10,000 here. So the full range of what you'll see on the machine. And then you've got natural frequency up here. So this is kind of how we measure one of the tuning aspects of the suspension. So ideally, you would want the same natural frequency across the weight range. So obviously we don't quite achieve this, but it's not a massive slope. There is some slope there, but again, this is the most basic system essentially. So the key way this works is you have a cylinder here. So this is essentially sits between your axle and your chassis. With the weight, the chassis pushing down on here, so heavier weight increases the pressure on the piston side. You've got an accumulator here. It's connected to both sides of the cylinder. Hence a regenerative system. So when the cylinder pushes down, you hit a bump, oil is forced into the accumulator, and when it rebounds upwards, it's pulled out. Now you have you've got disc packs here. These are Husco damping device. Essentially, it's a complex orifice. I'll get onto that in a minute. This provides the damping functionality. You've got two EHPVs, electro-hydraulic proportional valves. These are quite complex versions. They don't need to be as complex because these are variable. These give you the lockout functionality. So when both of these are closed, as shown, no power, your suspension's locked out. Oil cannot escape from the rod side or the piston side, and so has no connection to the accumulator. So you have rigid suspension. Your levelling functions are provided by, largely by these two cartridges. So when these are both operated, your pump, load sense here, margin set across this orifice gives you a fixed rate of flow to both sides of the cylinder, which will cause the cylinder to rise. We then want to lower that. The cartridge will close back to the position shown here. This one's still open. Oil then can pass through this orifice to tank, again in a controlled fashion based on how fast we want it to raise and lower. That will be controlled by a software algorithm based on the position sensor on the cylinder or the axle. So that's all the basic functions of it. So again, it's a basic system. It's only got one accumulator, which is how you make it relatively cheap. This does give you lockout. Different accumulators will give you different spring rates. And there's a few more complex things we can do using these EHPVs, which again I'll get onto in a minute. So, in our fairly basic installation, we use what we call a disc pack. This is a Husco patented device. We've been using these for about 10 years since we started using suspension valves, I believe. That's very small, so I think that's M22 for sort of scale sake lots. That's less than 1 inch in diameter. And what that does is it provides three functions in one. It provides a fixed orifice through the middle. It provides a check valve. Again, there's a check valve through the middle. And then it provides a relief valve element, which is actually a set of disc springs on one side. And all that combines together to give you a a curve, a pressure versus flow curve, as shown on the green line here. So the target for this is to give you a constant pressure drop, no matter what the speed of the impact, essentially. So you're driving down a road, you hit a bump slowly, or you hit a bump quickly, you want the same pressure, you want the same amount of damping. And with a fixed orifice, you're not going to get that. The slow bump, you've got very low flow, you're only going to get a very small pressure rise. You hit the bump quickly, you're going to get a very high flow, you're going to get a huge pressure rise, and essentially it's just not really going to move. So with the disc pack, that's fairly constant. It's not a completely straight line, but for the packaging and the cost, we can get very close to that and get very good performance. And that's obviously tunable, so we can do all kinds of things to play with the curve of that and give different damping characteristics. That still is ultimately a passive device, though. So the next step in complexity would be what we call a predictive damping system. So what we've got on the screen here, this is an actual situation that we came across and improved with an algorithm, software algorithm. So the red line here, this is suspension travel over time, so going over a set bump trap. The point here, this is us topping out on suspension. So you're hitting the bump stops. Now you'll be able to feel that on the machine. You'll be able to hear that on the machine. It's probably going to affect the life of the cylinder or of some components in there. It's certainly not desirable. Now in this situation, you've got the regen circuit shown a couple of pages ago, or something very similar to that, with the HPVs just wide open, fully connecting the accumulator to the cylinder. With disc packs in place, but even so, we'll still end up in this situation. So when we're suspended, those are wide open. So we created a software algorithm. Now the inputs for this were just things that were already on the CAN network on the machine. So shuttle lever position, that's the gear stick, forwards or backwards shuttle. Tractor wheel speed sensor, and also the position input, which obviously we're already looking at from a leveling point of view. So those are fed in, and within a couple of weeks we put together this algorithm. So it's relatively simple setup, which managed to limit the travel. So that's done by all those inputs are fed in, and they used to control the HPVs to set them to a point which is quite restrictive, but only when they need to be done. So yeah, you can eliminate the problem with a relatively simple setup and no additional instrumentation. So the next step from that is semi-active suspension, which can be achieved with basically a very similar setup. The key difference is you need an accelerometer on your chassis. So as well as all the other inputs, you can then, with that all being fed into an ECU, it can then calculate essentially the velocity of the chassis, the acceleration of the chassis, and of the wheel relative to it. So with that, essentially see what the machine is doing dynamically, and exactly how you would want to control the suspension. So you've got absolutely no dispatch on this, all damping done by the HPVs. The basics of it are that if the chassis is moving up and down, well, the HPVs will close down, restrict the flow, really damp the movement, and stop the chassis from moving. The chassis is moving very smoothly, but the wheels are bouncing up and down quite happily following the road. Well, that's brilliant. Your suspension's working great, and the HPVs will be wide open, maximising the connection to the accumulator, maximising your suspension ability. So you'll be absorbing as much of the inputs from the road as possible. So this basically gives you the best of both worlds. Gives you good damping and good ride control. So a little bit on suspension tuning. So this graph, well, these two graphs show transmissibility versus the disturbing frequency. So transmissibility, big word, it's a fairly simple concept. It's the ratio of which the loads are transmitted from the wheels to the cab in this case. So 1 across the middle, that's essentially a rigid connection. Less than 1, that means we're absorbing the loads, which is what we want to be doing, which is this negative, well, below 1 region here. But we can also, based on the natural frequency versus the input vibration frequency, cause excitation, amplification. So when you're around the natural frequency particularly, the inputs, you're actually getting worse loading, worse movement out of the cow. So obviously that's really what you don't want. So generally what we do to try and target get as much of the input vibrations covered by the suspension as possible is lower the natural frequency, which ultimately that means a low spring rate, which means soft suspension, which means you're going to travel a lot more for a given bump, which means you're going to want really long cylinders, and you know you're more at risk from hitting those end stops. So it has a lot of limitations. Now you can damp that. That will reduce the amplification. You can run at a slightly higher natural frequency. But I mean, as you can see, a fixed damping rate will not only damp your amplification region, but also damp your isolation region. So it'll remove the effects of your suspension. So obviously you can see the advantages of having a variable damping system. So I mean, ultimately, on a machine, every different tractor we look at differently. Like the loads that it'll see will be different, the geometry will be different, and so the way we tune it, in terms of damping, in terms of accumulator size and pressure, will be different every time. Double acting systems next. So this is one of our standard double acting systems. Key differences: we've got an accumulator on the rod side and an accumulator on the piston side. Apologies, that put the cylinders the other way up onto the previous example, but very easy to follow. There's quite a bit more complexity going on with this circuit than the previous one. That's largely just to drive the fact that we've got two accumulators, so we need two of these valves to control. We have a load sense shuttle so that we can drive the pump from either side, etc. One of the key features we have in here is we have a pressure reducing valve so that we can set a constant rod pressure. So the key areas of this is that because we have a different accumulator on either side, we can set a different precharge on either side and therefore a different spring rate, so that compression and rebound can be tuned differently. The fixed rod pressure, that helps to eliminate the low load problem of the low front axle load. So as that drops down, the fixed rod pressure so it also acts on the piston side, so it sets essentially a minimum that's going to see. So you can kind of see from our graph that you see, if you remember the regen version of this, has quite a bit of a slope to it. This is much flatter, particularly at this bottom end where it starts to flatten out. And that means that across the load range you're going to get a more predictable natural frequency and therefore better tuned suspension. Again, much like the previous systems, you can use EHPVs and disc packs to damp in different ways. Obviously, the more complex, the more cost involved generally, but the better the performance. So a few other different things you can do. You can have two different set pre-charge accumulators on the same side, well, either on a regen system or on the same side of a double acting system. Well, it has the increased cost of you needing two accumulators, but you can then get two different spring rates from the two different pre-charges, which gives you a broader range again, and will improve that curve that you see. Can possibly give you a bad spot in the middle of less ideal less ideal natural frequency, but it will give you a better overall range. Variable rod systems are some of the real finest, most complex hydropneumatic systems. This is where on a double acting circuit, instead of having a constant pressure on the rod side, you vary it so that when you've got that very low front load on the tractor, well, you can set that rod pressure quite high and really to counteract that. Whereas when the front load is quite low, you don't have to put that in there, which means your actual rod piston pressure range will be lower. Obviously, lower pressure range ultimately means a more flat curve in terms of the load of the machine versus the natural frequency. That can be done by either an electronic means or by a hydromechanical means. And again, as described, predictive damping, semi-active controls, you can use those on a double acting system and give you really well controlled system, which will put you right up on that performance score, but again, right up on the cost as well. So just to touch on cab suspension, most of the same principles as front axle suspension apply. You have smaller cylinders and you have less flow going through there. You have probably a less range in load changes. Obviously, farmers come in different loads, different sizes. You can also have more than one operator in a cab, so there's a bit of load change goes on there, but nowhere near as much as on a front axle with the implements and the ballast weights. So you can generally get away with a basic regen circuit. The one thing you may want to look into is having a 2-point system with different cylinders so that you can get control over roll and brake dive. And one last area of suspension we'll look at is loader boom. So you don't really see this so much on tractors, but theoretically you could fit them to. But it's quite common on wheel loaders and on backhoe loaders. So ultimately, when you're driving down the road with a full bucket, the machine can get quite unstable and bounce around. So you have systems that essentially just connect the head side of the cylinder to an accumulator when you're at a certain speed, leaving the rod side to tank. Now, there's no levelling function like you'd have on an agricultural system, because you still want the operator to be able to raise and lower that bucket at will. Otherwise, it could be quite dangerous. But one of the key features with this is that when you do slow down and the suspension switches off, your load's quite often going to change by a long way. You're either going to be emptying that bucket or you're going to be filling it up. You don't want the suspension to be engaged then, because you want to have good fine control. But then when you do start moving, the accumulator will have a few seconds ago perhaps been at a different pressure to the head than it is now. You were running with an empty bucket, you're now running with a full bucket, or you were running with a full bucket, you're now running with an empty bucket. And when the accumulator is re-engaged with the head side, that disparity will cause the bucket to either drop or bounce up. So some of the more advanced systems these days have a means of either changing the charge of the accumulator beforehand or afterwards, or before you re-engage, or dropping it down, or actually pre-charging it, or some other means of softening that handover. A little bit more about Husco and what we do. So we've got a full laboratory for testing hydraulics on site. We also manufacture, this is on our site in Runcorn, we also manufacture on site all our suspension product globally, I think on site in Runcorn. So we've got a lot of hardware readily available, parts we can just pick up off the factory floor. We've got machining on site that we can create prototype parts in just a few hours if needed. We've got endurance rigs, we've got data acquisition stuff for doing mobile testing on tractors, both hydraulic and vibration equipment. We've got test areas where we can run. We can generate our own software. What we can do, generate our own software. We've got our own controllers to use. And we are also in collaboration with what it says here is the UK's leading agricultural university, which is Harper Adams. Not you guys, I'm afraid. Which we use to do some test work and to give them projects to do to help us develop new ideas, essentially. Okay, thanks for your time.